Hi everyone, it's time to start talking about some real stats. Anyway, let's just go ahead and jump right into it, and we will be covering inferential statistics today. We're going to talk a little bit about the basics of it and how it all works. And I've already covered some of this, but I figured it's worth covering it again. And then we'll have some other lectures on more statistics, and then we'll talk about other things down the road. So again, remember, this is a review course of statistics, so it's less of a course on how to generate these than it is on how to interpret them. So a lot of this introductory stuff is just that. It's just an introductory about how to understand how this stuff works and getting you familiar with some of the terminology. So let's go. Here we go, inferential stats. Figure out what in the world does it mean. Quite simple. Can we generalize our findings beyond our sample? That's what we're making an inference, right? So we're going to infer from our sample to our population. Right? So the statistics that we're using are, the inferential statistics that we use will allow us to do this. And they'll tell us whether or not we can make this inference. And then all the other design criteria and things that we've talked about, talk about how do we make this inference from a causal level, right, from sample to the population, and whether or not the independent variable has an effect. Well, we're also now talking about will these things generalize, which is, in a sense, it's related to external validity, but it's also related to basically statistical conclusion validity, if you will. So a couple of notes here to talk about right off the bat. Number one, when you're dealing with a sample, we get a statistic for the sample. When we then generalize that to the population, it becomes a parameter. So if we talk about, let's say we get 100 people and we find out how many kids they have, and we say on average there's 2.5 kids, and that each person in this group had 2.5 children, that's a statistic. But if we then generalize that to the population, it becomes a population parameter. So a sample statistic and a population parameter, SSPP. That's the easy way to remember it. So let's move on and talk about sampling. All right. So right off the bat, random sampling. If at all possible, we need to be able to do this because all statistics are basically have a core logic of them that assumes random sampling. And as you've learned by now with some of the other content in this course, random samples are brutal to get, if not impossible. So we're going to assume that you got a random sample, and it drives me nuts to make that assumption because most of the time it's not actually accurate. So even if you did get a random sample, we do have something that we have to deal with called sampling error. There's no guarantee that our sample is going to accurately represent the population, even if it is random, right? So there is going to be some sampling error. In other words, what we're saying is that the measurement that we get in a sample is not going to be accurate at the population level. We know that. That's a guarantee. We've already talked about one of those adjustments that we do to make that happen, or to adjust for that inaccuracy when we're looking at the population variance versus the sample variance and those things. Right? So we're already dealing with the issue of sampling error there, but we need to understand the concept at a little bit bigger level in order to understand how the rest of all this stuff works. Anyway, so we know that our sample is not accurate at the population level. Usually this is simply because we have too small of a sample size. Right? And when we get 20 people or 40 people or 60 people, that's probably not going to be an accurate representation of, let's just say, the population of the United States at roughly 300 million. So we got to figure out what to do. Obviously, the number one thing to do to decrease sampling error would be to get a bigger sample, right? Of course, this assumes randomness. If we're just going to grab 3 of your friends or 20 of your friends or whatever and ask them some particular question, that's not random because they're your friends for a reason and they're different than the people that aren't your friends, and the people that aren't your friends wouldn't be represented, so therefore being able to generalize out to the population would be inaccurate. In other words, we're saying that it's an external validity issue. All right? So again, with random sampling, there's no guarantee that it's going to accurately represent the population. Usually that's because if you're doing a truly random sample, that sampling error is going to be due to not grabbing enough folks. And think about those people that are outliers, shall we say, those people that are on the extreme ends of that normal curve. Let's think of salaries. Somebody that makes nothing versus somebody that makes billions of dollars a year, right? So the chances of getting one of those people in your sample is slim to none because there's hardly any of them out there. There's very few of those folks out there. So actually grabbing one in your sample is going to be difficult if you're doing it randomly. Most of the time the random sample is going to come from the middle of that normal curve, as you've already learned about. That normal curve is, 68% of the population falls within one standard deviation of the mean, right? So that's the vast majority of the folks you're going to grab come from that area, which automatically sets us up with these external validity issues. So there's a lot of logical problems with this stuff, and one of the things that you're going to run into out there is when you're looking at the research and things and trying to decide on best practices and all that stuff in the field is this study going to work for the kids in my school? And the answer is maybe. It all depends on that sample. So you're trying to get a sample, or looking at those samples that are as close as possible to the characteristics of your school. And keep in mind that even if it isn't the same as your school, or the population or the sample is dramatically different, it doesn't mean that it won't work. It just means that it originally wasn't targeted at this population, or at your population or your sample. So you've got to, be a little bit leery of those types of things. So it's always something to look at when you're reading the articles: is who did this work with, and do you think that will represent the group that you're going to be working with? All right. So that normal curve thing, that 68%, the 95%, the 99%, and above. How does all that work? Well, it works pretty simply. Well, kinda. Anyway, let's start off with the fact that people really aren't that different. There's not that many differences between folks. We always in this culture we talk about how we're everybody's unique, just like everyone else, right? That type of thing. So everyone's unique. We're all different. We're all individuals. Yes, I get that. But when you start to really analyze how different we are on pretty much whatever variable you want to look at, we're not as different between. We're more similar than we are different, so to speak, right? So and because of that, we can then start to draw some conclusions. And because of the fact that there's a lot of similarities between us, we know that most people are going to fall into those central categories. Most people are not extreme Republican or extreme Democrat. Most people are kind of in the middle, right? And then there's some bias out towards it. There's some fewer people that are extreme on the ends. But most folks, they kind of go one way or the other depending on the situation and depending on the topic and those types of things. So in reality, most folks are going to fall in that middle. Right? So let's look at how this whole thing will work here. It'll take a minute, but we'll get there. Right? Let's assume that we take infinite samples. Right? So think of one sample as containing 100 people. And let's assume that our population of interest is the United States, and therefore we have about 300 million. So obviously we don't have an infinite sample of folks that we could choose from, but we've got a lot, right? An extraordinary amount. So let's take one sample of 100 people, and then we'll do some stuff with that. Now let's take another sample of 100 people, and let's take another sample of 100 people. And what we're going to start to do is do different things with each one of these samples. And if you think about it, if you took an infinite sample of a population, so if you took all 300 million people and you did a census on them, right, then what would tend to happen, depending on the thing that you're measuring, what would tend to happen would be that those people those scores would end up distributed normally, right? So it would end up in that bell curve. There's a lot, I'm hemming and hawing here because there's a lot of factors that affect that bell curve. In fact, there's a great book that, since y'all are in education, you should probably read it, which is called The Bell Curve, right? So take a look at that. There's a lot of challenges to that, and understand those challenges to that bell curve. But there's some interesting stuff going on there. Anyway, so let's assume that everything's accurate with what I'm saying here, and that if you take an infinite number of people from a particular population, that will create a normal distribution. That in itself, that infinite sample of people is called a theoretical sampling distribution. Right? So that is the not the hypothesis. That's the underlying assumption of how a particular sample will represent a population, right? So if we grab that entire population, it would be normally distributed. So then if we do a proper sample, our sample should be normally distributed as well. Notice I keep saying should be and could be and all those things. That's because there's, like I said earlier, a lot of factors that affect this stuff. So it's a theoretical sampling distribution, and we're going to use that as our basis for comparison. And that's what allows our inferential statistics to work, believe it or not, that we are assuming that at the population level it is going to be normally distributed. In fact, that becomes one of the biggest assumptions for all these statistics, is a normal distribution in terms of your sample, right? right? So because if at the population level we know it's going to, or with the theoretical sampling distribution is a normal curve, then we have to have that same sort of thing represented in our sample if our statistics are going to generalize to the population. So let's take it one step further with what I was getting at earlier with talking about those infinite number of samples, with talking about the samples themselves of the population and getting many levels of that. So let's see here. So let's get into what's called the central limit theorem. So the central limit theorem is based on this theoretical sampling distribution, and it basically says this: take one sample, get the mean of that sample, and plot that. Right? So, and when you do that, you create a sample. Again, you create your mean from your sample and you create a plot. So in other words, what we're going to do is we're going to create a frequency distribution or a histogram from the mean of each sample that we're going to get. Remember, this is theoretical. Okay, so now we're going to repeat 20 million times or whatever and do this thing ad nauseum until we have an unlimited number of samples that we could possibly get from our population. Right? The result is going to be also a normal curve that accurately represents the population. So we've got two different ways to deal with this normal curve, or to get at this normal curve thing. Number one, a theoretical sampling distribution is to take all people and plot them. You're going to end up with a normal curve. What you also see with the central limit theorem, and this actually produces a better normal curve, and this is actually a bit more measurable. It's still impossible because we have to take an infinite number of these things, right? So, or 20 million as it says. And then we plot the means of those, then we get a very nice normal distribution. And it turns out really pretty. Right? It is very symmetrical. It is almost a perfect normal distribution. So we're taking each individual sample and getting a mean from that and then plotting the means. The means become our data points in this case. Right? So from the central limit theorem's perspective, if we take enough samples, we're going to end up with a normal curve that accurately represents the population. So what that's telling you is it's getting at this concept of, what's the term? Not standard error, confidence intervals. Right? And now I'm not going to cover confidence intervals. It's well covered in your book, but I do want to say this about it, that the confidence intervals are related to this concept of the central limit theorem. And essentially what a confidence interval is saying that any one sample, right, how accurately does that one sample represent the population? Right? And what's the chance that that sample falls within a particular range of the overall? And what's the chance that the mean of that sample falls within a typical range of 1 standard deviation or 2 standard deviations or 3 standard deviations, that type of thing? So the central limit theorem ties in directly with that, with the confidence interval stuff. And you don't see confidence intervals reported very often, and they're useful for understanding some of the standard error. But there's an easier way to get at standard error, and we're going to get to that in a minute. Okay. So as we move, as the logic continues, the more you sample, the more likely you are to capture an accurate representation of the population parameter. So we keep grabbing samples and samples and samples and samples and doing this over and over and over again and replicating studies, and wow, we're eventually going to figure out this concept. We're going to figure out how this actually works at the population level, and we're going to figure out how accurate our mean is for any one sample with regard to that overall population based on the central limit theorem stuff. So that's going to ultimately get us at the standard error. But as the title says, we're not that good. In other words, we can't possibly do that. We can't get 20 million samples. We can't get 1,000 samples. Right? We're working with one sample, maybe two. We're working with very few numbers here, and we have to be able to find out how accurate that is. So that's going to get us to something called the standard error. And you notice I put standard error there in bigger letters and then of the mean, because it's useful to remember that we're talking about how accurate that mean is. So the standard error of the mean. Right? So let's figure out exactly what that is and how we can interpret that, because that's something that should always be reported in the journal articles that you'll be reading. The problem is people don't always report it, so you need to be able to figure out how to calculate it as well, and that way you know how accurate this particular study represents the population. Simply defined, the standard error is the standard deviation of the theoretical sampling distribution. So remember, theoretical sampling distribution, all the possible people, basically a census, right? And then find the standard deviation there. That is your standard error. right, of the mean of any given sample that you have. But that's, again, that's hypothetical, it's theoretical, we can't actually calculate that. What we can do, though, to calculate it is pretty easy. All right? So we're going to take a series of samples. Sample 1, sample 2, sample 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, whatever, right? And then how do we get to the standard error from that? Well, remember, the standard error is simply a standard deviation, so all we do is go back and calculate a standard deviation. So the sample means are now our x's. So all those x bars, right, all those means over there on the left, those are now our x's. Right? So we're going to plot all those, and we're going to use those means as our data points now. Right? So then we can calculate a mean of our sample means. So now we're calculating a mean, right? And then we're going to ultimately get to variance and standard deviation. Well, how do we do that? We talked about that before. We take the mean of our sample. Well, keep in mind now we're talking about sample means of means of sample means. But so we're going to get that mean of our sample means, so the mean of all these x bars, right? And then we're going to take each x bar and subtract the mean from it, right? And then we're going to that'll give us our deviations. And then we're going to square those deviations. We're going to sum those up, get sum of squares, the sum of the square deviations, and so on and so forth, which gets us to our variance. We take the square root of that variance, and then we have the standard deviation. Again, that becomes the standard error. It is the same thing. So the standard deviation of all of our sampling, of all of those samples that we have, is actually the standard error of the mean. But again, we're really not that good. We can't do that, right? It's impossible. Calculating that true standard error is truly impossible because it requires an infinite measuring of samples. You need to keep measuring sample after sample after sample after sample after sample. Right? So we have to do something else. We have to estimate it. And estimating the standard error is easier than all this stuff that I've talked about. Take your sample. I'm sorry, let's try that again. Take the standard deviation from your sample, divide it by the square root of n, and you have your standard error. That's all there is to it. Right? Notice that it becomes, if you start to analyze this statistic, okay, a standard deviation is the on average, how far is each data point from the mean of your sample, right? Now we're going to take essentially an average of that standard deviation, right? Because we're going to divide it by some value of n. But we're going to make that value of n really small, right? So standard deviation is always going to be smaller, or sorry, standard error is always going to be smaller than our standard deviation of the sample. And we know that that's going to be the case because we're dividing the standard deviation by something, but it's not going to be a lot smaller because we're dividing it by the square root of n. So if we have 100 samples, or if we have a standard deviation of 1, let's say 2, then we have 100 people in our sample, so the square root of 100 people is 10, so our standard deviation of 2 divided by 10 is what? It's going to be 0.2, right? So our standard error is going to be 0.2. So now we know how accurate that mean is, and how do we interpret that? We're saying that the mean of this sample is accurate plus or minus 0.2 at the population level, and then we could go on and talk about confidence intervals and those types of things. So the smaller you see that standard error, the more accurate you know that it is. Now, is there a rule of thumb about how small that standard error needs to be? No, not at all. Right? It's just because it's dependent on sample size and all these things, and you've got to take that into account. And there's way more to this, and if we start to think about what goes into a standard deviation and how that number changes and gets larger and smaller, and then the square root of n and how that would change if you have a larger sample and a smaller sample and all those things. And it ends up being that the larger the sample size you have, and it seems counterintuitive because we're dividing by the square root of n here, but the larger the sample size you have, typically speaking, the smaller your standard error is going to be. That's because the larger the sample size you have, you're going to end up with a smaller standard deviation as well, and then we're going to divide that by a particular number. So we'll keep getting this stuff smaller as things go on, and it just simply means that the bigger the sample you have, the more likely it's going to be accurate. But let's not forget our first basic point, which is that it's a random sample. We need to have that random sample because I don't care. And, if you sample 50 out of, if you sample 50 dentists, you should always ask the question, which 50 dentists did you sample in order to understand what's going on? They may be all the ones that work for Crest, so we shouldn't believe a thing that they're saying at this point because they're all working for the same people. And just because we have a larger sample size, we have 50 instead of 5, doesn't mean it's any more accurate. So again, the key for all this stuff to work is actually random sampling. And as you've been learning about in your quasi-experimental lectures, that is functionally an impossible thing to do. So at this point, you're probably sharing some of my frustrations, like, what in the world is the point if we can't do any of this stuff? And the point is really simple. As long as we get close, it's good enough. Statistics, they feel precise. But in reality, they're not as precise as what we tend to think they are. And when we think about parameters, remember stats at the population level, those are definitely not as accurate as what it feels like. And it feels great to get a number and say, oh, there's this in the population, and we can describe the particular rates of cancer, blah, blah, blah. It's like, okay, that's great. But we have to be cautious with that. And a couple of quotes from Mark Twain here should suffice for passing on my feeling about statistics. And the first one is, there's lies, damn lies, and statistics. And the other one, which is probably my favorite, is that statistics do not lie, but liars sure can figure. And on that note, I shall see you soon.